Welcome to two-dimensional motion and vectors. This is chapter 3. This is now section 3, and it's the third part of the multi-part video series. Just a word of note, as I was laying out section 3, I realized there are two aspects of projectile motion that we're going to look at. And because of that, I really felt that it's necessary to take this section and actually break it up into two shorter videos as opposed to presenting it all in one video. So this video will cover the first part of projectile motion, which is really what is called projectile motion without an initial vertical velocity. So there's no vertical velocity in this projectile. Now, what does that mean? Okay, well, what that means is think about standing on a bridge, looking down at the water. At your feet, there's a small rock. You kick the rock, it goes off the bridge, continues out for a little ways, falls down and splashes in the water some feet, some meters away from the bottom of the bridge, the base kind of directly underneath. If you had just picked it up and dropped it instead of kicking it, it would have dropped right at the base of the bridge, but this rock, because you kicked it, landed out a few feet from the bridge. That's the first type of motion. The other type is like a baseball, a softball, or something like that being thrown, where it goes initially up and out before it reaches kind of an apex to its trip and then goes out and down. And that would be like a full projectile motion, because that's almost like a true parabola, which is what projectiles actually travel, the type of motion that they have. So anyway, those are the two types, and we're going to look at the rock example first, where you're kicking a rock off of a bridge, which is really one half of a projectile motion as a parabola. It's half a parabola, so it's pretty straightforward. Okay, let's get to this. Okay, what do you want to do in this particular section? Well, you want to be able to recognize examples of projectile motion. You want to be able to describe the path as a parabola, and you want to be able to resolve the vectors into their components, very much like we can already do with vectors, and apply our various, what are called, remember, kinematic equations to solve the problems involving projectile motion, because now we're back to Unit 2 and Unit 3 equations, all those models that we had for velocity and acceleration. Remember that Unit 2 was constant velocity, and so we had constant velocity equations. They come back and we use them actually quite a bit. They were pretty straightforward. But now we're going to also bring in Unit 3, because we have also acceleration happening at the same time. And because of that, we want to bring in those Unit 3 equations, which all dealt with acceleration and situations involving changes in velocity. Okay, so some details on projectile motion. By using vector components, we can avoid having to multiply vectors, which is something that's, again, just beyond the scope of this class. We want to take components and use them to simplify the motion. We want to understand that projectiles, what are they? They are objects that are launched, thrown, or fall at some angle. So basically they have two aspects to their motion. They have an out component, kind of moving away. We call that the range, as far as how far it moves away from where it started to where it lands. And it has a height issue. There's a vertical component to it. So there's a horizontal and a vertical component to this motion at the same time. And so that's a projectile motion. Projectile motion is the two-dimensional motion under the influence of gravity. Without gravity, there will be no projectiles per se. The paths of all projectiles are parabolas, or some portion of a parabola, and these parabolas never fully flatten out. If a cliff were tall enough, even though it looks like the rock might be falling straight down, if it were kicked initially at the top of the cliff, it would never fully flatten out and have a completely 100% vertical motion, in the absence of things like air resistance and such that would alter a true parabolic path. And then lastly, projectiles have an initial horizontal velocity. So all the projectiles we'll talk about will have an initial out velocity, horizontal. Like you kick the rock. You kick that rock horizontally. You kick it out. That's the horizontal velocity we're talking about, and that's what it has initially. Okay, if you consider a motion of an object, so here we have this could literally be, instead of a cannonball, it could be the rock kicked off the bridge, right? Without gravity, that rock, this cannonball, would travel a straight line. I think my pen is activated and I can do a little bit of interaction here. So this cannonball would simply travel a straight line out from the cannon in the absence of gravity. With gravity, as I lost my place there, with gravity, what's going to happen is gravity, while this cannonball is actually moving away from the cannon, gravity pulls it down, and so instead of traveling a straight line, the cannonball is pulled down at the same time that it is moving out. And so two aspects to its motion. And of course, if it were just left to free fall by itself, this cannonball again, without any horizontal velocity, would actually just fall straight down. Okay, consider this example here. So we have a rock, it's going to simply drop straight off of a cliff and it's going to land in the water below 2.4 seconds later. Well, what do we know? Initially at the top of the cliff we can set the height at 0 and we'll figure out how high the cliff is based on that. We know gravity. Gravity is going to accelerate the rock downwards at negative 9.81 meters per second squared. We know that the initial velocity in the y direction is also 0 because we are dropping the rock. We are not throwing the rock, so we're just dropping it. So 0 at the beginning. And the time of fall is 2.4 seconds. And the question here is how high is, delta y, how high is the cliff? So in order to solve this question, I took a look at what I knew. I listed all of my givens up in here. And then I looked at what I was trying to solve for, which is the maximum y value. I have all the way back from Unit 3. As a matter of fact, Unit 3, we had this particular equation here. So this comes from Unit 3, and this is free fall. And so with Unit 3 free fall, we have this equation of the change in height, so delta y, equals the initial velocity in the y direction multiplied by the time plus 1/2 gravity multiplied by the time squared. Well, it turns out, of course, that the initial velocity in the y direction is 0, so we actually do not need that part of the expression. And that's what this is saying over here as well. So that part of the expression simply goes away, and all I did was then rewrite the equation down here, and I simplified it without the initial velocity aspect. So delta y equals 1/2 gravity multiplied by the time squared. I know what gravity is, and I knew the time from the problem itself. So the free fall aspect is only a function of gravity and how long it can fall for the height, or the height dictates how high or how long it can be in the air for. Either way, they all tie together. You do the math, and it turns out that the value, if you plug in a negative 9.81, it's going to be negative 28 meters. This is how far the rock falls. Therefore, the cliff is 28 meters tall. So this is how you can use free fall, two-dimensional motion. Well, this is actually one-dimensional motion at the moment. This is simply free fall, and this would have been Unit 3. We'll get into two-dimensional motion in a moment. Okay, so now let's talk about out and down, out and down. So in this case, instead, we have a rock kicked off of a cliff, and it lands in the water 2.4 seconds later, 15 meters from the base of the cliff. How high is the cliff? Well, this is really the same question, and because it's really the same question, I want to point out that even though this rock was given a velocity in the x direction out, therefore we ended up with a range, is what we typically call this. So the delta x here from the point of the base of the cliff to the point of where it splashed in the water is the range. That even though it's able to fall farther away from the cliff itself can still be measured to be 28 meters because an object that even with initial velocity that's falling downwards is in free fall. And because it's in free fall, the amount of time that it can be in free fall is directly related to the height of which it can fall for. So these two being tied together, a cliff that is 28 meters tall will allow free fall for 2.4 seconds. An object in free fall for 2.4 seconds can only fall 28 meters. So it's a cyclic supporting argument, if you will. Okay, well, that's not a problem there, but what more can we do with this? Okay, well, what we can actually do is we can actually figure out how fast we threw the rock. So what is the velocity that we gave the rock as we threw it? So if I come back up here to my diagram and activate my pen, so I'm up here at the guy. So what I'm looking for is the velocity in the x direction. So what was that allowed this rock to actually travel 15 meters from the base of the cliff to the point at which it splashed at, which is our delta x. So how can that happen? Well, what do we know now? We know that where am I? Okay, my givens are still up here. Good, I didn't erase them. We know that the time of flight is 2.4 seconds. We know that the delta x is also 15 meters. These two values together will allow us to solve for initial velocity. Well, because the velocity in the x direction is considered to be constant, we will be able to ignore air resistance. Okay, so we're going to ignore air resistance, which would slow an object down. So in the x direction, in the horizontal direction, we will always consider it to be constant velocity. So therefore, we can go back to our unit 2 equations, and we can use the constant velocity equations. So the velocity in the x direction, which is constant, equals simply delta x over delta t. Plugging and chugging in this particular case, 15 meters divided by 2.4 seconds will tell me that it has a constant velocity in the x direction of 6.25 meters, which, if you allow an object traveling at 6.25 meters to travel for 2.4 seconds, that object can move horizontally 15 meters. So this all supports itself. Very cool. What more can we do? Well, how about a motion map? Hey, pretty cool, huh? Like how the stuff all ties back together to the modeling. Okay, well, here I have, I've just erased some of the material here, so it's not as busy of a slide. All of my knowns are up here at this point. Well, if I wanted to do a motion map, I can actually do it right on this diagram, and I can then take advantage of this. So let's say this is 0 seconds. And then if I do only like 1 per second, I'm only going to get 2 dots here. So I'm going to do 1 every half second. So that would be 0 seconds. This would be half a second. This would be 1 second. This is going to be 1 1/2 seconds. And this would be 2 seconds. And then I can't really get 2 1/2 seconds because the time ends at 2.4 seconds. So that's all I get. So 0, 0.5, 1, 1.5, and 2, and all of these are seconds. So what is going on here? Well, check this out, okay? So we have velocity in the x direction, and this velocity is constant. So these arrows will always be identical. And if we had another arrow or another dot, we could do that. So all of these should be equally spaced. I might have a little bit of a fudge there, but you know, equally spaced and equal arrows. Now, there's an interesting thing here in the fact that we have vertical velocity. Up here at 0 seconds, we had no vertical velocity at all, but at 0.5 seconds, we had just a little bit. At 1 second, we had a little bit more. At 1 1/2 seconds, we had a little bit more. And then at 2 seconds, we had a lot more. And so now we actually can show vertical velocity as well. And, oh, wait, there's more. We also actually can then have acceleration vectors. And so in all cases, the acceleration here is gravity. So in all cases, we can actually show gravity with equal arrows. And remember that double arrowhead. And so gravity is always acting to pull this thing down. That's where the acceleration is, and why there's no acceleration in the x value And you see that that's all constant velocity, as opposed to we have acceleration in the y. So really neat stuff. I like this. And it's not difficult concepts. And to be honest with you, all of this stuff we have done before. All of this material we have covered. We're just pulling it together and using both constant and accelerating velocities at the same time, except that they are simply in different directions. Okay, now we have a rock being thrown off of a 100-meter cliff. So now we're on a bigger cliff. 100-meter cliff, and it's going to land 95 meters away. And the question simply here is, what is the velocity of the throw? And I don't have this one all worked out, so I guess I have to use my little cheat sheet here in front of me and work the problem with you. Excuse me. Okay, so what do I know? I've got my pen activated, right? And let me get some colors going here. Okay, so what I have is I have a height of a cliff at 100 meters. I have a range of 95 meters. So my range down here is 95 meters. My height of the cliff, I've already got it written over here, is 100. The initial velocity in the up here in the y direction is 0. So, you know, up and down it's 0. Gravity is always acting at negative 9.81, and I know that the velocity in the x direction is constant. Okay, so where do I start here? Well, remember that the range and the height of the cliff and the throw, all of this is equal or is related to the time of travel. And so do we have enough information to figure out the time of travel? If I want to know the constant velocity, you know, what is that equation? Well, let's show that really quick. So constant velocity in the x direction is equal to delta x over delta t. Well, I know x is 95 meters. I do not know vx, that's the question, but I don't know time. So that's what I'm going to have to find out first. Well, what else do I know? I know delta y, and I know that delta y is equal to the initial velocity in the y direction multiplied by the time plus 1/2 gravity multiplied by the time squared. Remember, this is a unit 3 equation, and because it's in free fall and initial velocity is 0, I can eliminate this part of the phrase, and I can then take this. I know delta y, I know gravity, I don't know time, my unknown. I can solve this. So let's rearrange and solve for time. So I'll just, I think, scoot over here so I have enough room. All right, so simplify. What do we have? Delta y equals 1/2 gravity multiplied by time squared, or delta t squared. Solving for time, let's just rearrange. So time equals, you'll have 2 delta y, as that 2 comes up to the y, just, you know, across the arrow, divided by gravity, because you divide both sides by gravity. And this was time squared, so this whole thing would be square rooted to solve for time itself. I have y, I have gravity, and multiply that by 2, square root it, and I have then a time of 4.52 seconds. Now that I know time, I can come back up and I can complete this equation here. So velocity in the x direction, being constant, is simply equal to its displacement multiplied by the time it was allowed to travel along that displacement, and it turns out that it is traveling at a very rapid 21 meters per second. And if you calculate that out, that's somewhat fast. All right, where else can we go from here? Boy, we're really cooking with some physics gas now, right? Okay, this is a pre-typed set of questions, and we are now dealing with, in your chapter, problem set 3D. So in and around problem set 3D, they always typically introduce a model or an equation, and they will describe and discuss it, maybe show an example, and then you'll have some practice problems based on that. And then, of course, leading from there is the worksheet series, like problem set D, problem set E, and all of those, which almost all, and maybe all the chapters in the textbook have, and you've dealt with several of those worksheets throughout the class. Okay, so this is vertical motion of a projectile that falls from rest. When it falls from rest, really, what we're talking about is it's going to be a variation. I can draw a variation of a cliff and a rock being kicked off, or it's going to be some kind of variation on this. It doesn't have to be a rock, it doesn't have to be a cannonball, but it's going to be some variation on that motion right there. And you'll have a height, you'll have a range, you'll have an initial velocity, you're going to have a time of free fall, and just all kinds of neat stuff. And of course, gravity is the accelerator downwards. So what is this over here? Well, these are a list of equations probably being pulled from Unit 3. So what do we have here? Well, the first one we have is the final velocity in the y direction, up and down, is simply a product of gravity multiplied by time if there is no initial velocity. We also know in using our Unit 3 equations, again modified for free fall, that the final velocity in the y direction, up and down, squared is equal to twice gravity times the displacement in the up and down direction. That is a modification of Vf squared equals Vi squared plus 2ay or 2ax, I think. If you check your formula cards, these should look familiar. I simply eliminated, so what have I eliminated here? Let me write it up. I have eliminated the fact that the initial velocity in the y direction is 0, so they just simply disappear from the equation set, and what you're left with are models for free fall. And then what do we have here? We have this third equation. The height is going to equal 1/2 gravity multiplied by the square of time. So that'll give you the height, or if you know the height, you can solve for the other unknown. Gravity will equal, of course we know what that is, and the initial velocity is always 0. And you can read the rest of that slide on your own. Okay, 3D, what about the horizontal motion of that projectile? Here again, if we have because I love drawing cliffs, they're so easy, right? There's my cliff, here's my rock, and there it goes over there. And we're now talking about Vx, okay? And that's going to be constant. So what is the x velocity is in the initial x direction, I guess, Vx, Vxi? It's going to be constant. We will neglect air resistance. So therefore, the displacement along the horizontal is only reliant upon the time of flight and the initial velocity that it is given in the horizontal or x direction. Therefore, we can use this equation down here, which is a Unit 2 equation. And that's we had many modifications, or we had like 3 variations off that equation. Okay, let's use an example. I can't remember whether this is out of your book or off of a worksheet, or if I modified it from some other source, but here we go. So the Royal Gorge Bridge is 321 meters above the Arkansas River. We kick a rock such that the magnitude of the horizontal displacement, its range, if you will, is 45 meters from the base of the bridge. We want to know what the speed of the rock was when it was kicked. Okay, I list my givens, if you go through the grasp method, right? So givens and requested. So my givens, I know the height of the bridge, I know the range of the rock kick, and I know that gravity operates in the up and down direction, and I could have a negative sign out there. My question here is, what is the initial velocity? Okay, so here's my equation for initial velocity. And the one thing that I don't know, of course, the 2 things that I don't know is I do not know this. This is what I'm trying to solve for, but I do not know time as well. So I can't use this equation yet. I will eventually use this equation, but I can't do it now. So is there a way I can use the other information that I know and solve for time? The answer is yes. I can use this equation. I know the height of the bridge, I know the time of travel, or excuse me, I know gravity, and I can solve for the time of travel. So I only have one unknown there. So I can take this and I can rearrange it down here, and I can solve for time. This is the very same arrangement we had just a moment ago. That square root symbol should actually go all the way over here. It's difficult to find the actual symbol to type it. And so once you do that, you now have the time, and then you can substitute that in for Vx equals delta x over delta t, and now you know the final velocity, or not the final, but the constant velocity of this object. All I have done down in this area here is just taken the equation and made a substitution so you can see kind of all the variables at once. But you can simply solve for the time and then go and plug and chug in this one. So continuing on, it actually solves on this particular side. So this would be the solve part of grasp. And it turns out that if you want that rock to hit 45 meters away from that bridge, you have to give it a speed of 5.56 meters per second in the horizontal direction. Now, that is really the end of this particular section. I didn't intend to go that far or go this long with it, but I had a good time talking about those examples. Now, what I want to do is I just wanted to introduce the fact that we will have a part 4 video, which is still section 3.3, but now what we're going to do is we're going to talk about, well, in the next video, we will talk about projectiles with initial velocity in the y direction that is greater than 0, so it's something other than 0. So what is that? Well, it is no longer, if I can draw it again, because I love my cliffs. Okay, so there's my cliff. So it is no longer this scenario right here, because the velocity in the y direction was 0 initially. So it's not this. It's going to be something like this, where the rock is thrown and it has some sort of an angle of throw, and it has some sort of initial velocity, and that initial velocity has both a horizontal component and it has a vertical component. And so we will have to take the initial velocity, if it's known, and break it up into horizontal and vertical components. So there's some trig. Or use the initial or the velocities in the x and y in order to find the initial velocity if we don't know that, and potentially whatever angle it was thrown at. We can also talk about the maximum height of the object. We could talk about the range of the object, so that would be the change in height. So there's a lot of things we can do if the y initial velocity is not 0. So that's what's going to come next in the second part of the videos for this particular. And this is just the last slide today for this one, and it simply talks about projectiles and parabolas, where we're going to talk now about out and up, out and down, happening at the same time in a true parabola. And the motion of a projectile is due to gravity. No gravity, you get straight line motion. With gravity, you get projectiles. The less air resistance that you have affecting the motion, then the more proper the parabolic motion will be. An interesting note, if an object lands at the same height that it started, so you know the altitude change, it may go up to 5 meters, but when it comes back down, it's at the same height that it started, then the max height can be considered by only half the motion, because like think about the soccer ball. It's on the ground down here, it's on the ground at the end, and so at the apex of the trip, it's halfway. You know, without air resistance, that's halfway. And we can use that because there's some things that happen right at the apex of the motion, which basically, think about this. If I do this and we consider eliminating all of this, what is this? This is a cliff and a rock. And so you can actually do like the cliff and rock situation, use some of those equations to find out what you want to know about, say, this ball in this half of the motion, and then back calculate it and kind of double everything. And then you figure out like the time of the whole trip instead of the time of half the trip. So it's neat. Okay, well, that's the introduction to the next part. And in the next part, I have several examples that I would like to work through with you in this kind of very rudimentary con-style academy, where I can kind of interact and solve the problem real time as opposed to showing it already typed and static. Okay, well, that's it for this one, and I will see you on the next, or hear you, or you'll hear me on the next video. I won't see you because, well, I can't. Thanks.